I'm greatly honored to give this DIMAT webinar and on the subject of measuring strength at high pressures using pressure shear plate impact experiments. So first I will give you some background and motivation why we are doing this work, and then I'll talk about the pressure shear plate impact experiments and extending the capability of this technique to high pressures. Then I will present some results on two materials, primarily on copper, which is a good model material to validate this technique and also look at some interesting phenomena at high pressures, and as well as a brief introduction to the high pressure behavior of magnesium, and then provide some summary of my talk. So why do we study this high pressure behavior? As we know, this audience knows very well that there are impacts and blast events, and there are many events which involve very high pressures and ranging from bird impact to hypervelocity impact. And there are many impact events which are some of them are shown here. Like the bird impact is a major problem for airliners. For example, this was the landing on what they call the Miracle on Hudson, which was a US Airways flight taking off from New York, which was hit by birds and then had to land on the river. Miraculously, everybody survived on this plane. And of course, the ballistics, armor, anti-armor problems are of great interest. And of course, hypervelocity impact, where it involves very, very high pressures, is also of interest. And the hypervelocity impact could be anywhere from 2 to 20 kilometers per second. And in this case, we reach very high pressures and also very high temperatures. So we want to understand high strain rate, high pressure phenomena in these cases. To model such problems, we need accurate constitutive models. And these constitutive models, as we know, is a function of strain rate, temperature, and other variables. And typically, we don't consider pressure at relatively nominal pressures of, say, in most metals, say in the order of 5 to 10 GPa. These pressure effects are not important, as we know from our work. But what we are interested in is in very, very high pressures. And as I mentioned, one of the applications is the hypervelocity impact. And you can imagine that the number of objects which are in the vicinity of the Earth, which is tracked every day, is like very large. And the small objects or bigger objects are going at velocities anywhere in the range of 5 to 25 kilometers per second. Of course, this can cause considerable damage if they impact space assets like the International Space Station. And here I show one of the examples where this was the Zarya section of the International Space Station was impacted by a micrometeorite impact. So this could have deleterious effects on structures, space structures, and obviously we know from the hypervelocity impact, we could have phase transformations, not only from solid to fluid to plasma, but also in undergoing materials undergoing solid to solid phase transformation and other associated phenomena. So we need to be able to understand such phenomena in great detail and able to model such phenomena. And of course, the other applications are sort of both terrestrial and also space applications. For example, in planetary science and also the recent energy applications such as creating fusion in the lab, this involved very, very high pressures. For example, in the creation of the moon, our own moon, about 4.5 billion years ago, this was due to the giant impact hypothesis, where there was an impact occurring on the proto-Earth, which created the moon. And in such cases, if you want to model such impacts, one need to be able to again know the high pressure behavior of materials, including strength and the flow behavior, to accurately model this phenomenon. In geophysical applications, these high pressures are very common. For example, if you look at the pressure at the earth of the core of the Earth, it's around 360 gigapascals. And this is like very high pressure, and one need to be able to model the material behavior at this very, very high pressure. So if you go to planets like Jupiter, this could approach 1 terapascal. And of course, as I mentioned earlier, that the inertial confinement fusion is one of the holy grails in creating clean energy. In this case, obviously, you want to produce the conditions in the sun which can approach 10 power 4 terapascals, and these are very large pressures. And one of the ways this fusion is being achieved is by focusing laser beams, 192 laser beams, on a Hall-rim and creating radiation, which will, the radiation pressure could collapse the fuel capsule, and you want to achieve very high pressures. And one of the limiting factors here are the hydrodynamic instabilities which develop in the shell, which doesn't allow this complete collapse, creating this very high pressure. So the strength of the material of the shell is important. Again, you want to understand the high pressure behavior at these extreme pressures. So obviously we are looking at a whole range of phenomena, and of course this audience knows very well that we are dealing with characterize the dynamic deformation by strain rates, and the strain rates of our interest, the most of our study is in the range of 10 power 3 to 10 power 9. And in this range, there are various phenomena could take place depending on the stress level. So here, the measure of the stress level is given by pressure normalized by the flow strength. And as you approach this very high pressures, which is hundreds of times of the flow strength or the yield stress, then interesting phenomena take place. And obviously these dynamic phenomena are dominated by shock waves, and we need to understand the strength and the viscosity of the material at these very high pressures. And also it can undergo fragmentation, shear banding, failure phenomena, as well as I mentioned, numerous phase transformation depending on the materials. And these phase transformations also play an important role in determining the strength of the materials and the flow behavior of these materials at these very high pressures. And obviously, if you go to extreme pressures, as the applications which I showed you, such as fusion, then you have chemical changes, and also you could have radiation emanating from this phenomena. So you want to understand this whole range of phenomena, and obviously one of the things which governs such phenomena such as fragmentation and failure is the strength of the material, and this is something which we are interested in understanding at high pressures. And obviously we have numerous techniques to address these problems, and we have all been looking at these problems. Of course, at low strain rates, one has this kind of either hydraulic or servo hydraulic machines or screw-driven machines to understand the behavioral strength of the materials, yield stress and flow behavior, which is very well characterized. And of course, another technique which is used for high pressures is the so-called diamond anvil cell technique. This is a very elegant technique which can go to very high pressures, but under quasi-static conditions. When you go to high pressures, then one goes to such as plate impact techniques. Obviously, many of us are working using the Kolsky bar or the Split-Hopkinson bar. In this case, the pressure is nominally zero. And because this limited uniaxial stress condition, and of course it can go to high strain rates on the order of 10 power 4 per second. With the recent advances in technology, that there are numerous facilities which are available, such as the Z machine at the Sandia National Labs, which can go to pressures on the order of 1 terapascal, and obviously the National Ignition Facility at the Lawrence Livermore National Lab. This can go to very high pressures, and people have looked at equation of state of materials in the terapascal regime. We are going to look at the plate impact technique, and the plate impact technique here we can generate high pressures. And primarily this plate impact technique has been used for studying the equation of state of materials and not unlimited studies on the strength behavior of materials, which we'll discuss in a few minutes. And the technique which is used in the normal plate impact technique is one uses such as PDV, the photon Doppler velocimetry, or VISAR, to measure the response either at the free surface or at the interface with the window to understand the evolution of the normal velocity profile from which one can obtain the equation of state. And this is a very well established technique, the shock wave technique, where you have an impactor impacting a target, and you generate a shock wave, and you generate uniaxial strain conditions. So there is only strain in the direction of the compression. And the stress, obviously, we have achieved close to a hydrodynamic state of stress. And here you have the normal stress and the transverse stresses. And due to the inertial confinement, you at very high pressures, you could have approach a hydrodynamic state of stress. Nevertheless, the strength of the material is important at this high pressures. That means the transverse stresses, the sigma y, sigma z, which are equal, differs from this normal stress, and that's what you have the shear stress. If you, for example, if you use the Tresca condition, but the strength of the material, it could be an order or few orders of magnitude smaller than the pressure. So this poses great challenges in measuring the strength of the material because it's a small number in comparison to the pressure of the material. So you need to have a way of directly assessing this strength of the material at these high pressures. So this is just showing what I just said in words, that if you look at the profile, the free surface particle velocity measured using a PDV or VISAR, you observe an elastic jump, the elastic precursor, which is the Hugoniot elastic limit. Then you have the elastic plastic shock wave, and then you reach the Hugoniot state where you approach the hydrostatic state of stress. And obviously then there is the release, and if the conditions are right, one can create the spall failure and so on. And the particle velocity is 1/2 the free surface velocity which you can obtain. As I mentioned, one of the primary uses for this such work is to create this equation of the so-called equation of state, which is the relation between the particle velocity and the shock wave speed. And the shock wave speed can be measured by the arrival time at the free surface, and the free surface velocity, the particle velocity, is measured by the free surface velocity. And then normally one sees that there is a linear US-UP relation. That's the linear relation between the shock wave speed and the particle velocity. And one can obtain the normal stress by using the jump conditions or the Rankine-Hugoniot conditions, using this formula of the density times the shock wave speed times the particle velocity. And many of us, obviously, one of the things which we're interested in is the flow strength of the material as a function of strain rate. And what we do is that as we approach the high strain rate regime beyond strain rates of about 10^3 per second, at least in metals, then you have the dislocation drag control mechanisms where you see a sharp rise in the flow strength of the material as a function of strain rate. As you approach strain rates of 10^6 to 10^9, then this flow strength would be extremely high. So this is usually such experiments are performed at nominally zero pressure. That means the pressure is very low, and then we are looking at the flow strength as a function of strain rate. So we are not the first ones to think about how to measure the strengths at high pressures, but there are many challenges associated with measuring strength at high pressures. So one of the very interesting techniques which is used both in the plate impact or in impact related experiments and as well as laser shock experiments is using the Rayleigh-Taylor or instabilities, whereby you put small perturbations on the surface of the material, and this is being shocked. And while being shocked, these perturbations grow due to the Rayleigh-Taylor instabilities or Rick-Meshkov instabilities. Then as you shock the material, if the material is strong or the strength is high, then the ripple growth will be small. If the material is weak or the low strength, then the ripple growth will be high. So this kind of gives you a qualitative measure of the strength of the material, and obviously one can do numerical simulations of this growth, instability growth, and then able to achieve high pressures and obtain the strength. But there is at the same time, there is high uncertainty of the coupling of strain rate and pressure, because as you can imagine, in this ripple growth, the strain rate and pressures vary or they're spatially non-uniform. Another popular technique is using the lateral gauges. That means, as I mentioned, that normally we can obtain from the free surface velocity measurements, we can obtain the normal stress in the direction of the compression, but the lateral stress we don't know. But one can effort lateral stress gauges such as the manganese gauges to measure the stress. And obviously using the such as the Tresca condition, one can obtain the shear strength of the material by sigma x minus sigma y over 2. And this is a direct measurement of stresses, but this works extremely well in brittle materials. But once you have ductility, then there is high uncertainty, and also there is the limitation of the pressure at which you cannot measure the strength. The technique which I'm going to describe was pioneered by Professor Rod Clifton at Brown University, and along with his co-workers, pioneered this technique about 40 years ago. And this technique is a very powerful technique which provides a direct measurement of the strength. And in this case, you impact a hard flyer plate on a sample which is sandwiched between two anvil plates, which is one called the front anvil and the rear anvil, and you measure the free surface response, and this is oblique impact. So due to the obliquity of the impact, you generate both normal and transverse waves, and the normal and transverse waves, the free surface velocity profiles are measured using normal and transverse displacement interferometers, and this will give you a direct measure using the characteristic analysis. One can get the complete stress strain behavior of the material, and this way one could decouple the strain rate and pressure effects. And I will describe this technique in some more detail in a minute. So this was the technique developed by Professor Clifton at Brown University, as I mentioned, 4 decades ago. And this involves impacting this hard plate against this target, which consists of these two anvil plates with a sample sandwiched in between. And so this is the distance time diagram, or the XT diagram here shown here. So this is the sample, this is the front anvil, this is the rear anvil. And we use the tungsten carbide anvil as an example. So you generate both normal and shear waves both in the anvil plates, in the target and the flyer plate. And the longitudinal waves, or the pressure waves, they propagate faster, and the shear wave trails. And when the pressure wave arrives, the normal longitudinal wave arrives at the interface at the sample. There is a thin sample sandwich, and it reverberates within this sample. So it attains sort of pressure equilibrium. So by the time the shear wave arrives, this is normally at a constant pressure, and also the advantage of such a sandwich technique is that you are creating a ramp loading. So that means you creating quasi-isentropic loading. That means your temperature increase can be moderated. And so you create essentially sort of a ramp loading in some sense. And then the shear wave comes here and it probes the strength of the material. So it is at a nominally high pressure, and then this shear wave probes the strength of the material, and the shear wave arrives at the rear surface. And in the meantime, the longitudinal wave reflects from the rear surface, reflects back, arrives at the interface, and then reflects back. So when the longitudinal wave arrives back at the sample, that means it has unloaded the sample because of the reflection from the free surface. Then the event is over. So essentially you have a shearing window from the time the shear wave arrives to until the normal reflection of the wave arrives back, the longitudinal wave arrives back. So we typically have about a 1 microsecond window of this thing. So here, as I mentioned, you make interferometric measurements of the normal velocity and also the transverse velocity. And in Professor Clifton's lab, this is done using a normal displacement interferometer and a transverse displacement interferometer, which was developed by Kim and Clifton. And so in this case, I mentioned because one can use the characteristic analysis, in this case, simple elastic characteristic analysis, and one can use the impedance, the normal impedance of the longitudinal impedance times the normal velocity. The particle velocity would give you the normal stress, and the shear stress similarly can be calculated using the shear impedance and the shear particle velocity. So the interesting relationship which is used here and exploited by this technique, which is why it is a direct measurement technique, is that the strain rate is simply given by the impact velocity impact transverse velocity, which is the boundary condition which is imposed, minus the free surface velocity, the transverse velocity, divided by the thickness of the sample. So this is kind of a simple shearing condition which you can infer from the elastic characteristic analysis. So once you have the shearing rate as a function of time, you can integrate this to get the shear strain, and obviously you have the shear stress. So you can plot the stress strain for at a nominally constant strain rate. But one of the challenges in this technique is that if we want to use the elastic characteristic analysis, then this is limited by the Hugoniot elastic limit of the anvil materials. So the best of the materials, things like tungsten carbide, this is limited to approximately about 10 gigapascals or so. The Hugoniot elastic limit limits the technique at which this elastic characteristic analysis can be used. So the work I'm going to describe is essentially extend this technique beyond the Hugoniot elastic limit. So we want to, as I mentioned, that we want to use this pressure shear plate impact experiments, which is an elegant technique, which has been very powerful in studying material behavior at high strain rates, but nominally low pressures on the order limited to about 10 gigapascals or so. We want to extend that beyond this regime. But there are numerous challenges associated with the technique, experimental setup, diagnostics, and how do you analyze this problem when you exceed the Hugoniot elastic limit. So these are the things which I'm going to describe in the next few minutes before I show you the results on copper and magnesium. So one of the things, as we can intuitively understand, especially this audience, that higher the velocity, higher the pressure. So we need to be able to launch projectiles at high velocities. So essentially what we have done at Caltech is to use a powder gun. So the powder gun is used, or the propellant gun is used for studying normal plate impact experiments, and this can launch projectiles on the order of 2 kilometers per second. So what we have done is, using this powder gun, which we use to do normal plate impact experiments, we have introduced a keyway to prevent the projectile from rotating. Because when you launch these projectiles, when we want to impact at this oblique angle, we cannot tolerate rotations in the projectile. Then you won't have this parallelism between the impact phases. So to prevent the rotation of the projectile, we introduce a keyway in the gun. So this is what we have done. And with the facility we have, we can launch projectiles between the range of 200 meters to 1500 meters per second. So normally, in the current plate impact experiments, the projectiles can be launched on the order of 400 to 500 meters per second using single stage gas guns. And also this is limited, as I mentioned, by the analysis of limiting it to about the Hugoniot elastic limit. And so I'm good. This is the first modification we did. And the second thing we had to do is we needed to have a robust measurement of the free surface velocities in this case. And which I should have mentioned earlier is there is a diffraction grating which is deposited at the rear surface of the sample, and this is where you probe measure the normal and transverse velocities. So what we have done is, to increase the robustness of the measurements, we have taken the PDB, the photonic Doppler velocimetry, and we have created a system where you can do heterodyne transverse velocimetry, so that we can measure both normal and the transverse free surface velocities using this photonic Doppler velocimetry techniques. So this is a fully fiber-based technique where you can see the 3 probes, which is the normal probe, and these are the transverse probes, the 2 probes, which are collecting the plus and minus 1 diffracted beams. And you can use the analysis, the traditional analysis, and then one can obtain from the transverse probes, one can obtain the transverse velocities using this heterodyne transverse velocimetry. And the normal probe is essentially the conventional PDB, or the photonic Doppler velocimetry. The diffraction grating provides a great advantage in creating this high fidelity measurements possible. And this, so in this case, the heterodyne transverse velocimetry probes, these are again the fiber probes, the normal probes, which are used in the normal measurements. So this is what we have done, and you can use the high-speed digital oscilloscopes to measure this. So this is a fully fiber-based system which is capable of measuring both the normal and the transverse velocities. So this, you can find the details of this transverse velocimetry in this Journal of Applied Physics paper. So now we take this technique, and then we can obviously we can launch the projectiles at these high velocities, and then we use this transverse combined normal and transverse velocimeter. So here I show you the. So we have also, because we can use nano fabrication techniques, we can write gratings to our design. So we have modified the design of the gratings so that we get high intensity beams. And in this case, we are also using 1550 nanometer wavelengths. So we need to modify the spacing of the grating and the profile of the grating and so on. And so here we can get high intensity beams. These are the 0th order, the 1st order, and the +1 and -1 diffraction order beams from this thing. So this is here illustrated using visible light diffraction. And as I mentioned, so we designed the experiment so that we can obtain the maximum shearing window and in the sample. So the sample is being sheared after being brought to a nominally constant pressure. So, but the problem still remains that we are exceeding the Ugolino elastic limits. So what do we do? How can we obtain? Now, what we are interested in is introducing this new variable, the pressure, as the flow stress as a function of strain rate, pressure, and temperature. So how do we include this? So we have developed the technique whereby we characterize the anvils. We know that the anvil plates are going to undergo inelastic deformation. So first we calibrate the anvils. So we calibrate the anvils by performing impact experiments using this oblique impact at nominally the same velocities as we would conduct the experiments, our pressure shear plate impact experiments on the sample. We conduct this at the similar velocities and similar pressures so that we can calibrate a material model. What do we mean by calibrate material model? I'm going to show you some of the details later, but essentially we are developing an inelastic or the flow stress as a function of strain rate and so on, and temperature and so on for these anvils by performing independent measurements. And this is first we calibrate the anvil material. So now the anvil material is completely characterized. And now we can conduct the experiments and we can again obtain the free surface velocity. And essentially our normal response, the normal response is dominated by the anvils because it's still the pressure is being transmitted across the sample and the same pressure wave is propagating. It's very slightly altered, only slightly altered by the presence of the sample. But the shearing response now is quite different from the symmetric experiments where we calibrate the anvils because the shearing response is now dominated by the sample. So this way we get the shearing response of the sample and we get both the normal and the transverse velocities. And so this is how we obtain the infer the strength of the material, again using numerical simulations. So what has really advanced, what makes us able to do this experiments, perform these experiments, and able to measure these flow stresses or obtain this, or compute these flow stresses is the number of advances which have taken place in instrumentation, in nanofabrication, and also in ability to perform high fidelity numerical simulations. So which didn't exist, a decade or two back. So this is what has made the thing possible. So the details of performing this plate impact experiments at high pressures has been published last year in the Journal of Dynamic Behavior of Materials. Now let me show you the calibration of this experiments. So these are the symmetric impact experiments on tungsten carbide, and here I show you ranging from 300 meters to 900 meters per second. And so the normal stress or the nominal pressure ranges from about 15 GPa to about 42 GPa. So here we show you the normal velocity and the transverse velocity. The transverse velocity, or in the green, this is just tungsten carbide on tungsten carbide, both the normal and the transverse velocity. And as you can see, we can clearly observe the HEL, the Hugoniot elastic limit. In this case, it's about 6.5 GPa. And then we can see the elastic plastic shock, which is steepening as it increases the pressure. And then you see the shock state, which is going from 14 to 42 GPa. So the transverse velocity is plotted here. And this is the normal velocity, as I mentioned, is ranges from about 300 to 900 meters per second. But the transverse velocity is much less. And here the obliquity angle is the skew angle ranges from 18 degrees to 3 degrees. As you see here, we reduce the angle, the skew angle, as we increase the pressure or the impact velocity to prevent sliding. And so when we go to low skew angles, we go as low as 3 degrees. And also we maintain very good tilt, less than 1 milliradian. So the transverse velocities themselves range from, say, about 40 meters per second to about 90 meters per second. So this is the range of the transverse velocities. And you can see this transverse velocities, this is directly giving you a measure of the flow strength of the tungsten carbide. So this is how we are able to calibrate the tungsten carbide. Now let me show you the calibration model for this thing. So we use a power law for this is for the tungsten carbide. So we do direct numerical simulations. So we can, this normal response is very well studied. And so we use, for the strength of the tungsten carbide, we use a power law for the strain hardening, a Cooper-Simons form for the strain rate hardening, and kind of Johnson-Cook kind of model for thermal softening. So here are shown the parameters. I'm not going to go into the details, so which you can see in the papers, the details of this. So this S is the slope of the USUP curve, and this is well known in the literature for the tungsten carbide. So now what do we do? So we can obtain we do the numerical simulations until we get the best match. And so you can see the details of the constants explained in this paper, in the recent paper just published. So here we see this is the tungsten carbide, which I showed you the normal and the transverse response. Now you can see the dashed lines or the simulations. So we can capture extremely well, obviously, the normal response. I want to emphasize that having this transverse response not only gives you the model, the strength model. Obviously, people use strength models even when you're modeling just normal plate impact experiments, the shock experiments. There, it is in some sense the parameters are unconstrained. The plastic parameters, the plasticity parameters, or the strength parameters are unconstrained. They're not so well constrained. When you have transverse velocity measurements together with the normal velocity measurements, then this is a highly constrained problem. So we can get very good representation of this material model. So we are confident that we have a very good material model for the tungsten carbide here. Now let me switch to discussing the results. I'm going to show you examples for two materials. One is a polycrystalline OFHC copper, which has been widely studied at high strain rates. So here what we are going to do is we are going to look at the strength at different pressures, but we are going to fix the strain rate nominally at 10 power 5 per second. And I will explain why we are limited in the strain rates in a minute. So once again, we use impact velocities from about 200 to about 900 per second. Again, the skew angle we range, in this case, range from 12 degrees to 3 degrees, the obliquity angle. The pressures range from 10 to 43 GPa, and the annual materials which we use and the plier material which we use are all tungsten carbide. So this tungsten carbide, as I mentioned, has the Hugoniot elastic limit of 6.5 GPa. The grain size in this OFHC copper, which is fully annealed, is about 100 microns or so. It's 110 microns in this case. Of course, we know the crystal structure for for the material copper is FCC. So the thickness of the sample is 170 microns, and the diameter is, which is limited by our gun, is the diameter of the target is about 30 millimeters. So now let me start showing you the results on the copper. So I plot the normal velocity and the transverse velocity. And the normal velocity is plotted here. Once again, you can see the Ogonio elastic limit. As I mentioned, the normal response is dominated by the tungsten carbide, and which is to be expected, which is just the pressure wave response. The pressure is completely transmitted by the copper sample, the thin copper sample. But now we look at the transverse velocity. The transverse velocity, even at 43 GPa, it's about 13 meters per second or so. So we need to be able to perform these measurements while the velocity, the normal velocity is around 900 meters per second. The transverse velocity is less than 15 meters per second. So you can see there's an order of magnitude difference in the transverse velocity. So we need to have this very accurate measurement system, this heterodyne transverse velocimetry, using this technology of the photonic Doppler velocimetry to be able to resolve such low velocities at this high impact speeds. So this essentially now, as in the conventional plate impact experiments developed by Clifton, we can't directly infer the strength of the material. Now we have to do additional numerical simulations, and this is the results of the copper are presented in the paper, in this paper, which was just published recently. So now we can start looking at the material models of the various material models. And so this is the pressure dependent model. So here we will use, this is for the copper, the tungsten carbide model, which I have already shown. Here I show you the model from the Steinberg-Guinan pressure dependent model. This is what we use for modeling the material model. And so here the shear modulus is dependent on pressure. This is a well-known phenomena, and also it's dependent on the temperature. And so these coefficients are given for the copper as described by the Steinberg-Guinan model. So these constants are available in the literature, but I will discuss what we have found a little bit later. And the shear modulus as a function of pressure has also been explored by this model, this very nice model. This is the Bulkowski-Greif-Preston model, which gives you a very nice expression for the shear modulus variation of the shear modulus. So if you look at the Steinberg-Guinan model, or the Steinberg-Cochran-Guinan model, and that's plotted in the black triangles, this is what is available in the literature. We have also looked at the Bulkowski-Greif-Preston model. They agree fairly well. So the slope is about 0.024 as a function of pressure. Now, the flow strength, on the other hand, is given by this model, and the flow strength is then again described by the variation of the flow strength with respect to pressure, and also the shear modulus with respect to the temperature. So one of the assumptions which is made in the Steinberg-Guinan model is that the variation of the shear modulus with the pressure and the variation of the the yield strength with pressure are assumed to be the one and the same. But when you make this assumption, we were not able to match the experimental results. So, if you make the same, that these two are the same, that the variation of the shear modulus with pressure and the variation of the yield strength with pressure, which is the usual assumption which is made, which is in the literature value, which is quoted as 28 terapascals, 28 per terapascal, then we are not able to match this transverse velocity. As I mentioned, the transverse velocity provides an excellent constraint on the strength model for the material. So this is why I think pressure shear plate impact experiment is a very powerful technique. Now, when we change the variation, then we don't assume it to be the same. We change the variation of the yield strength to the pressure to be about 65, which is about 2.6 times the value for the variation of the shear modulus with pressure. Then we see that the results are much better matched. So as I mentioned, one can always match, and this is well known to people who do simulations, that the normal response can be fitted with, with any kind of model for the response, inelastic response, or the flow strength model. But now the additional information we have is the transverse velocity, and then we can, using that the constants which I showed you, now we are able to fit the model with the transverse velocity is much better. So this gives us confidence that we are on the right track. Now, so we can obtain from the model. So then by fitting these experiments, we can obtain the shear stress as a function of the shear strain. And so this is shown for the 10 GPa, what the model tells us, and the strain rate here is about 2 times 10 power 5. And we want to have a sanity check of whether we are getting the right numbers. And these are results from the Clifton's experiments with Frucci. And here this is plotted shear strain as a function of shear stress. And here you can see this what is denoted as A. So here it's at the ambient temperature, and the strain rate is pretty close to what we have. And so the values are comparable. It's about 260 MPa or so at this nominal pressure of 10 GPa. Now, when we can plot the same thing for the response at different pressures. Then what you see is, you have a substantial increase in the in the shear stress, the flow stress as a function of pressure. So there's a considerable increase. We go from about 260 to about 630 GPa. So we can plot this now. We can look at the flow strength as a function of strain rate. What people have done is that, as I mentioned, that our strain rate is nominally constant, about 10 power 5 per second, but we are varying the pressure. So we are fixing the strain rate and looking at the increase in the pressure. So we are establishing the pressure dependence of the flow strength, and the strain rate as a function of strain rate, as you know, that there's this strong upturn. These are the Hopkinson-Barr experiments, these open circles which are shown here, and these are some of the plate impact experiments from Clifton's group, and some laser shock experiments here which are shown here. So as we increase the pressure, we can at a fixed strain rate, we see this considerable increase in the flow strength. This is again plotted on the log scale. As I mentioned, that our strain rate is limited at this 10 power 5 per second because now the anvils are yielding. They are not remaining elastic anymore, and this kind of limits the strain rate which we can achieve. And this is something which we are again working on, how to achieve these higher strain rates. As I mentioned, the conventional model assumes the Steinberg-Guénon, Cochrane-Guénon model assumes that we have the same dependence of the shear strength and the yield strength. But what we observe is that the yield strength changes considerably with respect to pressure, as opposed to what is normally assumed in the Steinberg-Guénon or in the literature. So I think this is a new finding because we make these direct measurements. So we wanted to understand what are the mechanisms which is leading to this pressure dependent strength. So we are performing molecular dynamic simulations. This is the work of Suraj Ravindran, who is currently performing the simulations. So here we can perform molecular dynamic simulations for copper, and this is performed using lamps. So we go from no pressure. So initially the microstructure is we apply pressure and then it's being sheared. So here, obviously, as we know that this is defect free initially. So we get this very high strength. And then we can look at the different dislocation structures which form using these MD simulations. And what we find is that we can find the yield strength. So we had 65 value of 65 in our experiments. So the molecular dynamic simulations are giving us a value of about 34 or so. And we can also obtain the scaling for the shear modulus from the molecular dynamic simulations, and they show the same values as assumed in the Steinberg-Guénon model, which is close to 34 per terapascal. As I mentioned, the Steinberg-Buchanan model assumes 28 per terapascal, and in the experiments we are observing that the yield strength scaling is on the order of 65 per terapascal, and this is yet to be resolved. And we believe one of the reasons has to do with the piles barrier at high pressures, how the piles Nabarro stress varies, and this is something we need to look at more detail in the core structure. And also the simulations which you have done are essentially single crystals. So we need to be able to account for grain boundaries and interfaces and other mechanisms associated with this. And this is something work in progress. So let me very briefly mention our work on magnesium. So we have looked at other materials, but I'm just going to show you very briefly on the magnesium. So the magnesium, once again, we perform experiments. As you know, magnesium is a lower strength material. And so here, once again, the shearing window is about 1 microsecond. And so we are compressing along the extrusion direction along the a-axis, and then we are shearing along the rolling radial direction. So here we only look at pressures, low pressures of 5 and 10 GPa. The grain size is about 70 microns. So if you look at the normal velocity, once again, I'm not going to go into the details. So the normal velocity and the transverse velocity, once again, we can use our model to fit this extremely well. Once again, having the transverse velocity, we are able to constrain the plasticity model extremely well. So this is at 5 and 10 GPa experiments. These are using steel anvils, so we are also using different anvils. So, but here also what we find is this is again plotting true stress as a function of true strain. So this is at 5 GPa and this is at 10 GPa. And so we find that there are some different mechanisms, operating mechanisms, because of there is a temperature increase which we need to account for due to the shock in the material, and also in the shock case that the material is pre-compressed before the shear wave arrives. So that is something also creates complications in the anisotropy of the material. So that is why, one of the surprises we had was that when we did split Hopkinson pressure bar experiments, it showed higher strength than the experiments in the plate impact experiments. So this is something which we have explained using the mechanisms operative under this thing. And this is due to the fact that when you have higher temperatures, it favors slip rather than twinning. So when you compress it along the axis, there should be extensive twinning, and this suppresses twinning, the increase in temperature, and this is shown in the literature. So we also did experiments on the pre-compression of the sample. When you pre-compress the sample, then the strength, what you observe in the split Hopkinson bar experiments, using kind of an S-shaped sample, the strength is lower before when you have no pre-compression. This sort of also explains why our strength at high pressures is lower than the split Hopkinson pressure bar experiments. So there's some rich physics in this kind of inducing anisotropy due to shock and then shearing the sample. So we are still trying to understand these mechanisms. So let me conclude. So I hope I have convinced you that that we can extend this pressure shear plate impact experiment to higher pressures. In this case, we have extended it to up to 50 GPa, and obviously we can take this to higher pressures if we can find good anvil materials and as well as other techniques to impact at higher velocity. So we have one of our main contributions have been to incorporate the anvil plasticity, and so we have shown that the material in the copper, the flow strength increases about 2.8 times or about 3 times when the pressure goes from about 10 to 40 GPa. And also the yield strength scaling for copper appears to be different from the strain strength, the shear strength scaling, which is assumed to be the same in the literature. And also I showed you very briefly that the strength of the magnesium is pressure dependent, and actually there are very interesting mechanisms which operate in this magnesium why this is the case, because this is because of the temperature increase and the reorientation of the crystals. So I have the pleasure of coming and talking to you, but this is really the work of many talented people in my group with the past and present. The high pressure extension to high pressure had posed numerous challenges, but these challenges didn't deter two really outstanding colleagues, Christian Kettenbeil and Zev Lavinger. So they made this technique possible in collaboration with Michael Mello. They developed this interferometric technique of developing this heterodyne transverse velocimetry. And the results which I've shown here is primarily from the work of a very talented postdoc in my group, Suraj Ravindran. And he has been responsible for doing the experiments on copper and magnesium, which I shared the results with you. And also he is assisted by a graduate student, recent graduate student, Vatsa Gandhi. And I thank you for listening, and I thank DIMAT for the great honor of inviting me to give this webinar. Thank you.